Hello, and welcome to my remotely delivered experience report about adaptive rubrics, making up the rubric after you see what the students did on their assignment for SIGCSE 2020. I am Marco Carmesino. I'm a postdoc at Simon Fraser University, and this is joint work with Mia Menes, a professor at University of California, San Diego. As educators, we have a goal. We want our students to be capable of rich, open-ended tasks. Tasks like programming large systems, mathematical proofs, writing large and expressive design documents, or writing at all, communicating complex ideas in prose. So we should assign them such tasks so they can practice them and get better at them. The problem with this is that richer tasks are harder to grade, meaning that they can be more time-consuming to grade, more error-prone, and much more feedback-intensive than a simple yes or no, right or wrong answer. How could we solve this problem? Machine learning? Well, no. The tasks are too rich to grade with a machine. Not the blockchain. And we don't have quantum computers yet, and even if we did, they probably wouldn't help with this. Let's step back and reconsider our goal. We want student engagement with rich, open-ended tasks, and the problem is that richer tasks are harder to grade well. What does that mean? We want consistent scores. If the students did roughly the same thing, they should get roughly the same score. We want actionable feedback. If the students made a certain type of mistake, we want to give them enough information to avoid that mistake in the future and do better. We want our feedback to be justified. We want it to relate to specific, concrete properties of what the students actually did. And we want the scores to reflect their progress over time as they get better at the learning objectives presented by the course. I can't give you a solution, but I can give you some kind of coping mechanism. And the buzzwords from the last slide won't help us, but we have our own buzzwords like streaming algorithms, human-in-the-loop algorithms, exploratory data analysis, cognitive science, and folksonomy. We are going to mix together all of these buzzwords and come up with a kind of algorithm for building rubrics after we've seen what the students did in response to a rich and open-ended task that was posed to them. The context in which we carried out this work was a large research university in a beautiful place where it's always sunny, the University of California, San Diego. We tried this in a core discrete mathematics course, so there were about 150 students per section. It's a required course, 2 to 4 sections per term, and those sections are taught together by the same course staff, so everybody gets roughly the same experience. We have a Gradescope site license, so that's how we collect and mark assignments. And the course staff is fairly large. We generally have 2 instructors delivering the lectures and making the final decisions about the course, 4 grad student TAs doing a mixture of marking and running discussion sections, and 9 undergraduate tutors running help sessions and also marking assignments. Let's see what happens when you grade in a course like this, or indeed any course, just ad hoc. The instructor has a global view of the assignment. She will generally pose the task, produce some kind of model solution, or give the okay to a model solution from the TAs or the graders, come up with some kind of rubric, and is the final decision point for judging the norms of the course. The grader has a local view of the assignment where they look at individual responses from the students, they score those responses, develop feedback for each response, and they refine the rubric as problems and mismatches might come up because the rubric was designed before seeing the assignments. This refinement and even this scoring often involves querying the instructor and receiving feedback. And it's important to note that this conversation process between grader and instructor is not structured. So grading will go on, there will be some kind of communication, and eventually it'll complete. Note also that this could be the same person. If you're running a smaller class and you're the instructor, you will switch between a local view and a global view of the assignment. So we think that our experience also applies to people running a course alone if they want to control how they switch from task to task in grading. So let's drill down into a specific problem that we have with the ad hoc method. It's called the online feedback dilemma. Here's a rubric. It consists of k binary items, so they just get true or false, and an assignment is considered marked once it has a true or a false assigned for each rubric item. Here's 233 responses to the assignment from the students. And in Gradescope, or whatever management system you're using for these responses, we traverse them in some order, and we're checking them off as we've filled out the rubric. At time step 134, when we're looking at the 134th assignment in traversal order, a funny thing could happen to whoever's grading the assignments. They could realize that rubric item 2 would be much better if it was changed to R2 prime. It would grade this assignment so much better. So what if we make that change? Well, obviously, we have a problem. What about every assignment that we saw before assignment 134, before that insight was achieved about the rubric? One of two things could happen. First, the change could be small, and we would only have to go back and change a few assignments to the new item. That would be good for us. That would be a relief. Alternately, the change could be pretty dramatic to previous assignments. We could realize something very informative about the previous change. We would have to relabel a whole bunch of assignments, and that's bad. Let's go into this problem in prose now. Basically, earlier students get a worse rubric task fit, or we are forced to restart the grading process whenever the rubric improves enough, whatever that means. And the response order will matter for inducing this problem. Responses could be in submission order, which is what Gradescope does, I believe, and that's a problem because maybe earlier submissions are from more confident students and they make different types of mistakes from students later on in the submission order. They could be alphabetical, which that would be good. That would maybe be pretty close to random, which is what we'd really want. Or they could be by lecture or discussion section, which again, there might be specific mistakes that are correlated with specific lectures and discussion sections. So we might not see certain patterns until it's almost too late in the traversal order to go back and make the rubric better. What are we going to do about this? Well, I'm a theoretical computer scientist, and when you have a hammer, everything looks like a nail. So we're going to appeal to algorithm design. We're going to make up a model of flinging a bunch of data at a human, a stream of items, and to make up a model, we need computational resources. Humans have limited memory and attention. The student responses are the stream of items that we're going to be flinging at the human. And we also have limited restarts. We have a limited willingness to say, okay, throw out what we're doing and we'll regrade. We can do that maybe a couple of times. And we have randomized insight. That kind of orange event might happen where we look at an assignment and realize something like, oh, we can really improve the rubric if we rewrite this item in light of this assignment that I've just seen. So that's roughly the model that we're thinking of. Okay. What do we want to do with this? Well, we want to minimize task switching. We want to split the grading work between the work of recognizing patterns in the assignment, assigning rubric items to student responses, and actually generating their feedback. If we do these things separately, maybe we can do a better job on each one and be more efficient while we do that. We want to reduce the strain on working memory. We don't want to be holding many patterns in our mind at once or looking for a lot of things in the assignments. We want to converse efficiently with the instructor because interaction with the instructor, that also takes time. That takes up course staff time that could be devoted to interacting directly with students or doing something else. And we want to respond well to central tendencies of the solution population. So if a lot of students made a particular mistake, we want to write good feedback to that mistake so as many students as possible benefit from the same high quality of feedback. These are all related to cognitive load. We know from cognitive science that when humans task switch frequently, their cognitive performance degrades. So we want to minimize all of these strains on the graders and indeed the grader course staff's cognitive load while making sure that we have high quality grading feedback, responding well to what most students did. To accomplish this, we're going to use the following algorithm. First, we explore the distribution of student work by tagging a subsample, the same way that you would tag your music collection with increasingly specific genres like rock down to prog rock or folk rock or punk rock. Then we count the tags. We want to find common solution techniques that the students used, common mistakes that the students made, and common questions about the question, so that when we talk to the instructor, or when the grader talks to the instructor, they know how to prioritize their question. Questions could be about the correctness of an assignment, the equivalence of two different responses, or the relative importance of features inside of an assignment. Does this mistake really matter according to the course norms? And that's something that the instructor needs to decide, not the grader. Then we get those high utility questions answered and design a rubric that's based on the model solution, the data that we extracted from tagging a course sample, and the course norms. Let's see how that works out in the same white space that we saw the online feedback dilemma work out. Once again, we have our 233 responses, but this time we're also going to have something called a tag workspace, so we don't strain the working memory of the grader too hard. We're going to keep our tags there, and we're going to execute the following algorithm. First, read the abstract rubric that the instructor writes that lays out course norms and what we're looking for in terms of solution quality. Then tag the model solution. Try and answer the question of why is the model solution a good solution according to this rubric. Maybe they substituted some definition correctly, or they have a good inductive hypothesis if it's an induction question. Then we draw a sample from our 233 responses, just 50, and we tag each response. This is just pattern recognition. So if the grader looks at a response and says, oh, they didn't apply the inductive hypothesis, that sounds like a mistake in a good tag, just throw that into the tag workspace. And each time the grader visits a new response, they check the tag workspace to say, okay, does any pattern that I've detected in the past apply here? And they also think, do I see any new patterns in this one response? So this reduces strain on working memory. And we'll build up a number of tags, like say, question tags like, oh, I'm not sure if this alternative inductive hypothesis is okay. This assignment has that tag. And the grader will continue this process, maybe finding a specific type of algebra mistake. Also, I found it useful to have a question mark tag for assignments that are very difficult to parse. We can use that tag to see how many assignments are just completely baffling and save those until the end, when the grader has built up a great deal of context for the assignment. And by then, those responses are often much easier to handle and they become clear, whereas previously they were just very confusing. And those students get the feedback they need, individuated. Finally, once we've traversed the whole subsample and generated these tags, we count and filter the tags. So maybe that bad algebra mistake, maybe that specific mistake only occurred in a couple of assignments. So that's not too important. We can just drop it from the tag workspace. On the other hand, that alternative inductive hypothesis, 14 students did that. So with these numbers of assignments and size of the subsample, that's a pretty significant fraction. So we want to make sure that the grader asks the instructor, is that inductive hypothesis okay? Because we could expect to see that in the larger population of student responses based on its representation in the subsample. So what's the experience of using this like for the grader and for the instructor? For the instructor, who again has a global perspective on this, she makes up the model solution still, but the questions that she sees are sharp questions. Not only are they shaped by popularity, they're important because they have to do with a lot of assignments, but the tags help refine them. And again, she applies norm judgment in response to these questions. The grader has predictable restarts. They know that they're going to go through this subsample maybe a couple of times if they're still confused, but once they're grading the whole collection of responses, they're working with a set of tags that works well, and they're going to stream through in one pass. That's good. That promotes a feeling of momentum and reduces cognitive load on executive function. The grader will help draft the rubric by building these tags and associating feedback with them, and the grader gets to batch similar tasks. This extends even to communication. We can schedule questions about the subsample, do all of those at once, and we can schedule a meeting for rubric development where the grader comes with a draft rubric based on their tags and feedback for the instructor to help them improve and then use for the final assignment. Finally, I'd like to observe that one of the things that emerges in communication between an instructor and a grader when you're using this method is the tags become a shared vocabulary of nouns and adjectives for describing common patterns in student responses to the problem. And that's very useful for sharpening questions and understanding how students are doing in the course overall without the instructor having to look at every single assignment. And once again, I'd like to note that we can view this as scheduling shifts between types of work for the same person if you are working on a course yourself, and that will reduce cognitive load on you because your work is more predictable and more structured, hopefully. So in future and ongoing work, first, we need better tooling. The software that drives this right now is Gradescope and a bunch of scripts and system automation software that I wrote. So we would really like to get better plugins, better support in Gradescope or other learning management systems. So we really need better tooling to make this popular and adopted. We need to try it. We need to do randomized controlled trials to see if there are measurable improvements in someone's experience for using this. This is an experience report, not yet an experimental study. So we would really like to do that. Earlier, I sort of waved my hands about a stream human model. We could do a theoretical analysis of the interaction between cognitive science, so assumptions about limitations on human cognitive resources, and algorithm design that underlie this in order to improve it and perhaps generalize it to more than one grader working on the same assignment at once. Because right now, our assumptions sort of rely on a single grader building up a lot of mental context for recognizing what patterns are important as they traverse a subsample of the student responses. And finally, if all of those above bullets succeed, we'll need to produce how-to guides and successful resources for explaining how to do this to hopefully people in the CS education community. So thank you very much for your time and attention. I hope that everyone is staying safe and healthy, and I hope that I can continue working on grading systems for CS courses in the future. Thanks again. Bye.